You are welcome to today's edition. Last week, Thursday, we started discussing correlation. We'll wrap it up today. By next tomorrow, we'll discuss regression. So today, we'll wrap all the correlation. I'm sure, I wouldn't know if everybody that is here now were around, but let me just quickly run through what we first of all discussed. Correlation in everyday life, it denotes some form of association. In statistical terms, we use correlation to denote association between two quantitative variables. We established that fact last week. It has to do with two quantitative variables. Though it's possible, even if the variable was not quantitative originally, in case of ordinal variable, you can allot number like or the Likert scale. Whichever way, there must be number, because correlation has to do with number. So those two variables you are trying to correlate, they must have number. So either the number their original value, or is number that you code. In case of a ordinal scale, where you just give arbitrary number 1, 2, 3, 4, 5, just ranking. But the only things that the one that are continuous variable and the ranking, they are different. The correlation are different, but whichever way, correlation has to do with two quantitative variables. We also assume that the association is linear. That is, one variable increases or decreases in a fixed amount for a unit increase or decrease in one variable. That is, if variable A increased by 2 and variable 3 now correspondingly increased by 3. If variable A increased by another 2, that other one will increase by another 3. That's what it means linear. Now, regression involves both estimating best straight line to summarize the association. We'll not be talking about regression, but this is for correlation. By next tomorrow, we'll talk about regression. Correlation describes the sense of association between two variables. Correlation is completely symmetrical in the sense that if you say correlation of A and B, it's the same thing as B and A. In correlation, there's nothing like dependent variable or independent variable. Both of them, they are just variables that you are seeing the strength of association. It is when you now go into regression, you have to decide which one is dependent, which one is independent. And by convention, if you are plotting that you are relating two variables, X and Y. Of course, now you cannot call both of them X, unless you want to call it X1 and X2. But when you come to correlation, you can call it X1 and X2, two variables. But when it comes to regression, you call it X and Y because it is assumed by convention X is the independent variable, while Y is the dependent variable. That is, Y is the outcome variable. So if the two variables are related, it means that when one changes by a certain amount, the other changes on an average of a certain amount also. If Y represents the dependent variable and X independent variable, the relationship is described as the regression of Y on X. We'll talk much about regression later. Then for us to understand concept of, for you to understand the origin of correlation per se, how it came, you must understand the concept of covariance. You get to know that correlation actually came from covariance. Covariance is a measure of how much two random variables vary together. That is, two variables, as one change, the other, how much does this one change? How they vary together. It's quite different from variance, but it's similar also. Variance talk about how one variable varies among groups, while covariance talk about how the two variables vary. So if you have variable X and Y now, the X-axis is variance because it varies among the subject or population. Then Y has its own variance because Y also varies. But if parameters they vary together for one reason or the other, that varying together is called covariance. And of course, you can now plot the variation on a plane figure. That is, when you have horizontal and vertical. You cannot plot, you can only represent one variable on a line. But for you to have horizontal and vertical, that shows that you are having two variables. So in a situation where we talk about covariance, how two variables vary together, you can plot them on the graph. Look at these three graphs now. This one that just come down, it means that as one variable increases, the other one decreases. While the one that goes up means as one variable increases, the other one increases. So the first one talk about the variable move in opposite direction, while this last third one talk about the variable move in the same direction. So they vary in the same direction, the other one they vary in opposite direction. So if they don't have covariance, they don't covary at all. Okay, the first one, they covary in opposite direction. That is, as one increases, the other one decreases. If this one that is decreasing, the other one will increase. So they are in opposite direction, they covary in opposite direction. While this one, the one that goes up, means that they covary in the same direction. This one that is scattered means that there's no covariance between them. Now, let's illustrate variance and covariance. Now, this is an example I gave it before also, but let's just quickly rush through it. This one is an example that is looking at covariance, variance, and covariance. We have two variables here. The first one, variable X, add the number of advert worked for a program, a product. Maybe after the company manufacture a product, they try to advertise. So then the second one is the packet of the product bought. So we have 5 people now, number 1, 2, 3 to 5. These are the number of adverts watched by each of them, and these are the number of packet of the product bought. And these are the means and the standard deviation. Now I want to see, do the number of advert watch co-vary with the number of packet of the product bought? So pictorially, we can depict it. If we plot both of them, the blue is the advert watch, the green graph is the packet bought. Now you will see that the mean, if you look at the mean for advert watch is 5.4. Look at the line, that is blue line is the mean for advert watch, 5.4. And you see in between 4 and 6, 5.4. Then the mean for the packet bought is 11. On the table, look at it between 10 and 12, it's 11. Now, you will see each point, how they differ from the mean. Of course, those ones that are below the mean, is negative difference. They are below the mean. So you now connect them from their position to the mean. The difference is negative because they are below, because you actually, in trying to calculate deviation, you remove the mean from the value. So those value, individual values that are less than the mean, when you remove mean from them, it will be negative. Those are the ones that are below. Those ones that are above the mean, they are above. Their difference is positive. When you remove mean from something bigger, it is positive. You can now see for both of them, it shows that they have covariance, they covary positively. As one increases, the other one decreases. How do I know? By looking at the graph, you see that all those ones on the two graphs, all those ones that are below the mean, they are in the same direction. That is, the first 3 observations are below the mean for each of them, and the last 2 observations are above the mean. That shows that they vary in the same direction. If let's say they vary in opposite direction, what will happen is that as these first 3 packet board are below the mean, then as these first 3 advert watch are below the mean, the packet wall will be above the mean. The first 3 packet ball will be above the mean, and as the last 2 packet advert watch is above the mean, the last 2 packet ball will be below the mean. So in that case, they'll be facing opposite direction. And this one is facing down, the first 3 is facing down, the other first 3 for this one will face up. As this last 2 is facing up, this one will be facing down, facing it. That shows that they vary in opposite direction. But if they don't even vary at all, if there's no covariance, you will not see a particular pattern. You just haphazard. This one can be in this direction, the other one in this direction. You cannot see any good pattern. That's just a pictorial view of that. But if you want to quantify it mathematically, you know that variance, if you talk about the variance of x, the formula for variance is x, you know that x minus sigma summation of x minus s bar all over n minus 1. N minus 1 is the degree of freedom. So the x now, the variance for x itself, it will be x minus s bar square. If you want to talk about the variance for y also, you go to the y minus sigma, y minus y bar square over n minus 1. But here we talk about the covariance, how the two of them vary together, the covariance. In that sense, so in calculating the covariance will now be x minus l bar y minus r. Instead of you having, you know, if you split this x minus l bar square now, it just means x minus l bar times x minus l bar, x bar. So one of it s will be for x, the other one will be for y in covariance. That's why covariance is x minus s bar into y minus y bar. This is the covariance. If you are to calculate the covariance now, all you need to do, look at it, is to sum x minus s bar, then sum y minus y bar, multiply the two, and divide by 4. That was what we did. Because look at the x minus s bar, the multiplication of the two, the summation of it. You now know you will have multiplied both of them anyway. You will have multiplied both of the x minus s bar into y minus y bar. Summation make it 17. Divided by 4, the sample size is 5. That is n minus 1 is 4. So this will be the covariance. Now, the covariance you see, as you see the figure, is not so useful for anything. Because there is a problem with interpreting it. If you do it for another thing now, it will give you just figure. How do you interpret it? It has no much meaning because whatever value you are going to get depends on the unit of measurement. If you are dealing with distance, you are dealing with all those in that have big figure. Maybe distance 1,600 kilometers, 16 hours, or 24 hours. All those things, when you are dealing with big figure, it will give you big figure also. If you are dealing with something like weight and height, or height in meter and something small, it will give you small figure. So you see that it depends, the value depends on the unit of measurement. And also, it also depends on the value of each of the measurement we are dealing with. So it's not standardized, it's not something that is universal. To overcome this, the intelligent people, what they can do is what they did for normal distribution, where they know that many things that follow normal distribution, if you plot the graph, so it gives you a bell-shaped graph, normal distribution graph, but the shape of the graph, whatever graph you plot, depends on the unit. Now depends how you go to plot it. It now depends on the unit. So remember your physics when you are plotting graph, you have to explain the unit. Maybe 1 kilometer represents 1 centimeter. You have to be saying all those things. It's the same thing if you have to do that for normal distribution. So intelligent people now came, okay, instead of talking about that, they now converted it to z-score. That is, they converted each value into the number of standard deviation from the mean by dividing the deviation from the mean by the standard deviation. For each, I gave an example. If the mean weight is 70 and standard deviation is 10, anybody that weighs 80, mean 70 minus 80 will be 20 over 10. That's plus 2 standard deviation, because the difference between 70 and 18 will be 10 rather. So when 10, so when you divide the 10 by 10, which is the standard deviation, it's 1. If the person weighs 90, the difference between 70, which is the mean, and 90 is 20. That 20 you divide by standard deviation, it has cancelled the unit out. It gives you 2. That should have the person that weighs 90 is 2 standard deviation above the mean. The person that weighs 80 is 1 standard deviation above the mean. It's the same thing here. If you look at it, our variance is all about x minus s bar, y minus y bar, the deviation of each, the mean the deviation of the y and x from their mean. So If you look at, so if you now want to standardize it, to cancel out the unit, you now divide it by standard deviation of X and Y. So if you look at it, correlation is a standardized covariance in the sense that look at the covariance now. If you now divide by the standard deviation of, look at it, this is standard deviation. No, standard deviation is square root of variance. So if you calculate variance of X will be sigma X minus S bar square over M minus 1. If you find the square root, that is the square root. The same thing for the Y. Standard deviation of Y is
the square root of the
square, yes,
square root of the variance.
Y minus Y square over M minus 1, then square root. So these two now, this you are seeing the standard deviation, this for X, standard deviation for Y. So, and this is the covariance. So if you now divide the change the structure, you know that this this M minus 1, square root of M minus 1, and square root of cancel M minus 1. Because square root of M, if you multiply the square root of M minus 1 and square root of M, it will be equal to M minus 1, which cancel this M minus 1. In that case now, so the N minus 1 issue is how? You now say X minus S by Y minus 1 all over this. And that is the formula for correlation, basic correlation. So it can be written in another form like this, where it's a little bit complex form. They give you the same answer, but just know that this is the formula. Know that the correlation does not have unit. If you remember, because the same thing you put X minus Y is the one numerator. It's the same X minus Y that denominator here. The unit has cancelled out. No, it's a ratio, it has no unit. Anything that you got by dividing two things of this same unit has no unit. It's like if somebody divide 400 kilometer over 400 or 4 meter and 4 kilometer. 400 kilometer divided by 4 kilometer is 100. It's not 100 kilometers because kilometer has cut off kilometer. It's a ratio. It is when you say 400 kilometer divided by 4 hours, you can say 100 kilometers per hour, which is the speed. Yeah, so in as much that both numerator and denominator are the kilometer or are the same quantity, so whatever you get has no unit. It's the same thing that's happening here. So correlation has no unit, and there's something, it can never be greater than 1 because the numerator can never be greater than the denominator. The numerator and denominator can be the same, but the numerator can never be greater than the denominator. So the what really happens is that this numerator will be varying from 0 to 1. It can never be greater. You know, that is why the correlation is from 0 to 1. So the numerator can vary from 0 up to the denominator, but it cannot be greater than the denominator. And that's why it can never be greater than 1. So the best thing is to be equal to the denominator. So in that case, when you divide that value by the value, it gives you 1. So it ranges from 0 to 1. So the only thing is that, so that is correlation for you. So we'll now begin to explain every other properties of correlation. So just know that correlation is standardized covariance. So that is why it's universal. So it's used in engineering, in any field, astronomy, any field of life. You're like odds ratio, relative risk, z-score, all those things, they are ratio because you have already divided by removing unit. So in that case, it's now universal. Now, let's move on. The meaning of correlation now. The degree of linear association between two variables. The strength of the association is summarized by the correlation coefficient. What we just got from covariance now is correlation coefficient. There is a type. We'll discuss that one further. The correlation coefficient is a dimensionless quantity ranging from -1 to +1. I already said it is dimensionless. It has no unit. A positive correlation is one in which both variable increases and decreases together. A negative correlation is one in which both, as one variable increases, the other decreases. I actually use an analogy. You remember the mathematics in secondary school, direct proportion, inverse proportion, they call it variation. Direct proportion, inverse proportion. Two things, quantity are directly proportional. As one increase, the other one increase. Why two quantity are inversely proportional. As one increase, the other one decrease. That one that was increasing, if it start decreasing, the other one will increase. So there's change. So they will move in opposite direction. That is inverse proportion. And I also talk about for more illustration, those of you that did physics and chemistry, remember Sharp's laws and Boss law. Sharp's law talk about the temperature and pressure of gas are directly proportional. That is, as you increase the temperature, the pressure increases. So both of them increases. They are like positive correlation. All those direct proportion, that's positive correlation. In statistics, that's what we call positive correlation. But in mathematics, they call it direct proportion. While the Boss law that talk about volume and pressure being inversely proportional. As you increase volume, pressure decreases. As you decrease volume, pressure increases. That is inverse proportion. That is the negative correlation. So in statistics now, the inverse proportion is actually negative correlation, while direct proportion is positive correlation. So it's just a nomenclature. So most of some of those terms you see in statistics are borrowed from mathematics. So now, meaning, so you can have value when the variables are exactly linearly related, the coefficient equal +1 or -1. That is, when you say nearly, exactly linearly, all the time, as this one increase, this one will increase. As this one increase, or as this one increase, this one will decrease by that amount. That shows that they are perfectly linearly related. That is, if you try to plot it, you will see it on a straight line. If it's always like that, all the points will be on the straight line. All the points will be on the straight line. That is perfect. You're going to see the example. Know that the correlation coefficient is unaffected by unit of measurement. We have already said it. The square of the correlation coefficient, okay, leave this one for regression. The square of correlation coefficient give the proportion of variation of one variable explained by the other. This one you leave for regression. You explain it when you get to regression. Now, meaning of correlation still. Correlation, just to create the mental picture, I've already said it that it's a standardized covariance. That is, is covariant, the numerator, varied by standard deviation of the two variables we are dealing with. So if you are talking of correlation between X and Y, is the correlation between X and Y is covariance of X and Y over the standard deviation of X and Y. That's all. Now look at it. When it is perfectly positive, can you see? It will slope up like this. It will be going up, and all of them will be on the line. If it is perfectly negative, this is the last one. It will be going down. That is, can you see? If you look at the first point now, the first one is always maximal at the vertical, but is minimal as the horizontal axis. As this vertical is going down and as you reducing, this one is increasing. Can you see? So whenever the slope is slant downward to the right, that is negative slope. It means that is negative correlation. That is inverse proportion. But if it slope upward like the first one, that is positive correlation, which is direct proportion. So perfect are because they are online. But when they are not perfect, they still high. Look at it. You still know that this thing, though it's not in one line, but they are going up. That is high positive correlation. Look at high negative correlation. They are going down, though they are not online. You can see low positive correlation, low negative correlation. So you can see how scatter the graph is. We determine whether it's a strong or very low, high or low. But the direction, either it's going down or it's going up, to tell you whether it's positive or negative. But when there's no pattern at all, I cannot even see is it going up, is it going, it just scatter. That is zero, no correlation. Zero, no correlation. Now, the correlation coefficient, that center of association we are talking of, is measured by the coefficient. That is, what is that in that quantify it. Now, the one we have derived from covariance is called Pearson correlation coefficient or product moment. Pearson product moment correlation coefficient. A product moment just means that if you look at it, by multiplying deviation of X and division of Y divided by multiplication of their standard deviation. So that's why it's product moment. So it was first described by Pearson, who was the first person to describe chi-square also. So now, is actually that person correlation coefficient is appropriate for continuous variable. But when the variable is not continuous, in continuous variable, so it usually follow normal distribution, and if that is a form of parametric test measure, so product moment person correlation, which is denoted as R, is a parametric statistic in the sense that it is assumed that what you are using for the follow normal distribution. But there are situations where you cannot assume that. They said that maybe that particular thing normally follow normal distribution, but for that data set, it didn't follow, or that particular thing does not even follow normal distribution. Like for example, now, Likert scale, anything on Likert scale do not follow normal distribution naturally. Anything on Likert scale, and that is all you can use. And sometimes also something that is whole number, like a number of something, unless the sample size is very high, otherwise you not follow normal distribution. So in those situations, it will not be appropriate to even use person correlation. So there are other forms of correlation. We are going to look at Spearman correlation described by Spearman. Then Kendall's correlation. Those ones, they just give Spearman require ordinal data for both variables. That is, both variables there must be ordinal. Ordinal means that, for example, when you score something, maybe disease severity, severe, like all this cancer, where differentiated, not differentiated, you just grade it on a scale of 3 or 4. For you to have ordinal scale, you must have at least three categories. You cannot have two categories and say it's ordinal scale. It's not possible. So ordinal scale has to be, but it doesn't mean that if something is 3 categories, ordinal scale. No. There's something like socioeconomic status that is ordinal scale, because we know that we usually say upper, middle, lower. We know that upper is higher than middle, higher than lower. Your educational system is ordinal, because when you say no education, primary, secondary, tertiary, so you know that there is gradient. So those are ordinal scale. In that case, you can use, even though naturally they are not number, but you can put 1, 2, 3, 4, and just that is like you have already coded, rank it. It's an ordinal data. So that's what you use Spearman for. You also use Kendall for such thing, but in a situation where the sample size is small and there are a lot of tyrant. That is when there are a lot of value that are, like for example, if you put something on like education on a scale of 1 to 4, no education, primary, secondary, tertiary, and majority have that secondary. So it's a lot of tyrant. Most of them is the secondary. So it's a lot of tyrant. So Kendall will be appropriate. Then we have the last two are quite interesting. I think I talked about it last week also. They are quite interesting. They are called point biserial correlation. Point biserial is a situation where you have one continuous variable, now have one dichotomous variable. What do you mean by dichotomous variable? Variable that is only 2 categories. We have already talked about rank. When you say something, you cannot have 2 categories and say you are having something rank. No. For something to be rank set, it has to have at least 3 categories. So every quantitative variable, if you range them, you group them into more than 2 groups, automatically is rank. But this one is dichotomous in the sense that you can just have the dichotomous that have 2 possible values, and they come in 2 ways. They may occur naturally like that, like when you say something that requires yes or no, or male and female. Male and female, naturally there are 2 sets. There are many things that are like that, night and day, right hand and left hand. Well, no, right and left, up and down, no, small and big. Anything that occur in 2, that is dichotomous. Then that one, since they occur naturally in group, it is called discrete dichotomous variable. Discrete, in the sense that it's discrete. There is no underlying continuum. It's not got it from number. Was there for sex now? It's discrete dichotomous variable. Alive or dead is discrete dichotomous variable. As opposed to the second type, which is continuous dichotomous variable. Imagine if you do blood sugar. After you do blood sugar, blood sugar is a continuous variable. You now have a cutoff. Anybody that have 126 and above is diabetes. The rest non-diabetic. So you see now you have now divided them based on the blood results. You have a cutoff. You see, diabetic, non-diabetic. So diabetic, non-diabetic is two categories. It's dichotomous, but is a continuous dichotomous variable because it has an underlying number you use to do the cutoff. The same thing with anemia. When you do hemoglobin concentration of PCV, you have a cutoff. Anything below certain value is anemia. Then the rest not anemia. So the same thing with blood sugar pressure also. Then the same thing with examination also. You can say you want to divide people into pass or fail, pass or fail. You have a cutoff point, pass, fail. So that cutoff point is what the differentiate pass from fail. Do that pass from do that fail. So in that case, it's a continuous dichotomous variable. So when that first one, which is discrete dichotomous variable, when we are doing correlation between a continuous variable on its own together with that one, that discrete dichotomous variable, the one that does not have underlying continuum, it is called point by serial correlation. But if it is between the continuous variable and a continuous dichotomous variable, like when you make blood sugar, you say diabetic, not diabetic, or obese, not obese. That is, and you are correlating with a continuous variable on its own. That is biserial correlation. Now, look at person and sperma. Maybe it's interesting that both of them were biologists and they contributed a lot to statistics together with Fisher. I think both of them were, well, I don't know Fisher, but I know it was a biologist, but person was a geneticist. Fisher was a geneticist. Gattin was a geneticist. You know, a lot of people that contributed to statistics, they were biologists and some other social scientists that contributed. So let's quickly look at this first one. How do you compute it? How do you compute person correlation? Look at an example. We have an example here of 15 children, and you try to correlate the height of each children with their pulmonary death space. So how do you do it? It's very simple. If you look at this formula, you don't look at the formula. There's nothing complex there. It's very simple. You already established the fact that is a covariance divided by standard deviation. So all you need to do is that x minus s bar. That is, this is x, the height, the y is the pulmonary death space. So we have look at their means are there. Calculate their means, summation and mean. If you sum everything, divide by the number, give you the mean. So x minus s bar mean you remove mean from each value. So that's the first. This x is the height, y is the pulmonary death space. X minus s bar means you are removing mean of s from each of them. Give you this. Y minus y bar, you are removing mean of y from each value. So, so x minus s bar is multiplied by y minus y bar. Multiply these two, it give you this, which form the numerator of this when you sum it together. And x minus s bar squared. That is, if you square this, because you want to know for you to calculate the standard deviation, you must know the variance and now find the square root. The same thing, y minus y bar, for you to calculate the standard deviation, you must know the variance. So if you, by the time you add it together now, the square root of these two is the standard deviation. Like this one now, the summation of this, then divided by the, anyway, we are not dividing, summation of this, the square root of this one, it was give you, these are the square root, this is square root. So if we look at it now, 5426.6 will be numerator divided by square root of the standard deviation, that is this one, square root of summation of s minus s bar square, and the second one, square root of summation of y minus y bar square. When you do it, it gives you, this is the correlation. Now, if you have your question, just be writing it down. So you can do significant test for it, and this is just a way of showing if this correlation is significant. Put it to test. This is the formula. T is t-test you used to do, and the formula is different from the t-test you know, but it's the same t-test. So just all you need to do, look at it. R is correlation, square root of n minus n is the sample size minus 2 over 1 minus r square. Give you this. But you understand that testing is significant because when you do this one, t-test, if you look at the p-value, it's less than or equal to 0.05. It shows that it's significant. But testing correlation is useless because the reason is that usually give you the p-value is not useful. So they don't usually use p-value to interpret correlation in the sense that the value of the p-value either is going to be significant or not, depends on the sample size. Small correlation with big sample size will be significant. While big correlation with small sample size may not be significant. So you can see. So rather, towards the end, you see how to interpret. There's a way to interpret apart from the p-value. So you don't use the p-value. So testing for the significance of it is not useful. Now, let's look at the Spearman-Brand correlation. Most of the advances you see in statistics started with quantitative variable, like what happened now to the issue of this correlation that it was gotten from covariance. So it has to do with two quantitative variables, and that is why that R square is in R rather this Pearson correlation is the first. Then because that particular Pearson correlation is not appropriate for anything that does not follow normal distribution or any rank data, so intelligent people like Spearman also came up with this. So what he does is to just do some ranking, and it's more appropriate, as I've said it, when you are talking about count, like number of children, number of people, because number of something is discrete. It doesn't have decimal. They cannot ask you how many children you have. You can say 2.3. No, you cannot have that. So other categorical data like you want to use like pain score, pain score where you put on like scale. Those are the things you use. Look at it. The same example we use now. Let's use the same example of height and pulmonary death rate. You can see. Let's examine. It's possible that even by the time you do the height and you now discover the pulmonary death rate, they are not normally distributed. You feel that Spearman Pearson correlation is not appropriate. So in that case, you want to use Spearman. All you need to look at the formula is 1 into 6 sigma d square. All you need, look at n here. N is just sample size. All you need to calculate there is the d, the difference between the rank. What it does is to rank the two values for the two variables. Look at the height, it's already ranked here. Look at the rank of the height 1, 2 to 15. A rank means that the smallest followed by this, the highest have 15. Now, to rank the second one, pulmonary death rate, that's rank. So, you know, if you arrange the first one by the rank, you cannot arrange the second one by the rank. You just have to put, okay, what is the rank of this one? Because you must not change it because each person, this number 1, this is the rank. Yes, you have to know this is the height, this is the pulmonary death rate. So if you decide to even arrange the first one according to the rank, you cannot arrange the second one like that. The only thing is just for you to put the rank. So, and the way you do the rank, the smallest 1, that one is smallest 1. The second to the smallest, the next one will be 43, 2. The third one is 44, 3. The next one, there are 2 of them. Okay, the next one is 45, 4. The next one, there are 2 of them, which is 56. Look at the 56, 56. So they are supposed to be 5 and 6. So because they are tied, you have to now add 5 and 6 and divide by 2, making 5.5. Now give each of them 5.5. So the next, so in that case, there is no number 6. No, the next one will be number 7. Then it's just like going in school. If two people became first, there's no second position. We will have third position. Or if two people become second, no third position. We only have fourth position. So now, you now say, okay, 50, the next one will be 58. So that's how the ranking. So this one D mean the difference in the rank. That is, remove one from the other. Yeah, you don't even bother. You can remove number 1 from the second one from the, it doesn't really matter. Because you are going to square it here. When you square it here, negative, because negative will cancel. You know, if you remove this from this, the one that will give you negative will be different from if you remove this one. But since you are going to square it, it cancels out. So when you look at the difference, you now square it. When you square it, this is the sum. We now sum the d square. D is the difference. So there's the d square in the formula. You just put it. You see, the Spearman is a little bit higher than Pearson for the same data. Because Pearson is 0.846, Spearman is 0.892. So that is how to calculate. So there's this third one, Kendall. Kendall correlation, that one, little where is it tricky? It's about ranking also, but the formula looks simple. But it's what you do before the formula. Using the formula is one may be confusing. So you look at the formula Kendall. Though there are 3 types. There are 3 types of this Kendall. But this one that is being used mostly, and most software they give type B, Kendall type B. There's type A, there's type C. But this is the one that is being used. So what this one means, C minus D. C means concordant. D means discordant. C, concordant minus discordant over concordant plus discordant. It looks like the formula for McNeman. Yes, for like McNeman. They look funny. So how you do it? It's very simple. So here now, just okay. Let's say we arrange the first one. This is the first rank. This ranking now is a director. Some people came for interview. The director did his own ranking, and the manager did his own ranking. That's slight different in their ranking. We want to see, do their ranking correlate? So they don't need to be exactly the same thing before they correlate. So yeah, their ranking. This is the ranking for the director. This is the ranking for the second one is for the manager. So if you want to know, calculate the concordance are the one. When you choose you stay by that second round. You look at it against this first rank. You pick one of the second rank. You look at this against the first rank. So below, from every one above, that is from that rank above that rank, how many are above this one? If they are above it, that shows that there's concordant. The number of this one that are above of all this one, from second one down, that above this first of this rank to this second rank will be the number that are above this one, be the concordant. That's how you do it. Okay, like for this one now, how many are above? If you count, all of them are 12. But when from here down will be 11 of them. But these 2 is not above these 2. So if from this 13, you count is 10. 10 that are concordant. When you come to this one, from these 3 to 12 now, all of them are above this one. So 10 that are concordant. If you count it. For this one, how many are above this 4? This 4 is not part of it. It's not above. So you now start counting from there. You count it, there are 8. 1, 2, 3, 4, 5, 6, 7, 8. This, how many are above this? The same thing. They are above this here. Is from this place. There are 6. Okay, this one, there are 3 or 8 also from here. This one, there are 6 from somewhere. This one, there are 6 of them. This one, there are 4 of them from here down. This one, there are 4 of them from here down. This one, there are 2 of them, this and this. and this one, two of them, this and this one, there's no one, because this only 12 that is here is the same value, so 0. So that is discorder. You know, in discorder, you know how many that are above. But in concorder rather, in discorder, how many are equal to or below? Equal to or below. And for this one now, these two, from here down, it's only these two that is equal to these two. That is why it's 1. For this one, from here down, there's no one that is equal to or less than 1. So that is 0. From this one, it's only this 4 that is equal to 4 or less. That is why it's 1. Here, there's no one that is above or equal to, below or equal to 3. Here, only 6 is equal to 6. 1. Here, no one is below 5. That's why 0. Here, only 8 is below 8. That's why 1. Here, no one is below 7. That's why 0. Here, only 10 is equal to 10. That's why it's 1. Here, no one is below 9. That's why it's 0. Here, this 12, only this 12 is. That's why it's 1. So you now had, I don't know why that thing left. You now had the concorder and discordant together. I think this one is 6. I don't know, maybe it's in remove. This one is supposed to be 6. 6. So if you say 6, now if you apply this formula, concorder, C minus 0 over C plus 0, 60 minus 6 over 60 plus 6, which is 54 over 6. So the correlation, the Kendall tag is 0.818. So if you run it, the people that, you know, we did the workshop, the first batch of the workshop last week, the people that came, we run the same thing, and the SPSS give us the same value, even though that's what we calculated. So then points by Syria. Actually this one, nobody bother, because it's actually even though all this, the explanation here is more descriptive. It is Syria because it's a correlation between a continuous variable and this bicomponents. So the Pearson correlation, if you run in SPSS, it gives you the same thing. It's a Pearson correlation that actually better. Theoretically, it says proportion of the cases. This is the formula. R is equal to square root of Q over Y. Proportion of the cases that fall into the larger category. Proportion of the cases that fall into the smaller category, that's Q. Y is the ordinate of normal distribution at the point where there is P% of the area on the side. So this one is talking about the Z-score. So now just know that in SPSS it runs this as what do I call it? Pearson correlation. Now let's quickly look at how do we interpretation. Many people come, if you know, we already said that it's useless calculating P value for correlation. Whatever, even if the computer give it to you, don't ever interpret your result based on that, because it's closely affected by the sample size. So intelligent people came with some, like a good fold, talk about the rule of thumb, say that if it's less than or equal to 0, less than 0.2, negligible correlation, between 0.2 to 0.4, low relationship, 0.4 to 0.7, moderate, 0.7 to 0.9, high, then greater than 9, very high. 1, we know is perfect. Some other people, different people come, but they are all closely related by the way they explain. Look at this one. So perfect 1. No, it can be positive, it can be negative. Look at it. Look at this graph. Now this is positive on this line. Perfect. This is -1 because it's negative. This is strong, 0.7 to 1. This is negative strong, minus this. So it's the same thing, because the correlation has to do with the direction, which is the sign, and the value, the strength of the association. So what minus means that both of them move in opposite direction. If it is positive, it means that both of them move in the same direction. moderate 0.5 to 0.75, and weak 0.25 to 0.5. So if less than 0.2, you say it's negligible, not like what we saw here, that is negligible. So I think okay, the last one I just want to say is the type of correlation. Though we describe the different type of correlation coefficient, but when you are calculating the different way, but though the commonest one, which we actually calculate, is bivariate, which is also called zero order correlation. Bivariate is also called zero order correlation. Then we ask about partial correlation, semi-partial. We just try to depict it. This first one now is the bivariate, the normal one we know. We are looking at the correlation between A and Y. How do they? So as even B is there, you just leave B. B may have relationship with any of them, but you didn't bother yourself about B. Now that is bivariate or zero order correlation. But if you want to do partial correlation, in that case, you are looking at a correlation between A and B, but you are trying to control for the effect B has on A. Can you see now? B and B as no, sorry, this is semi-partial. This is semi-partial. So the effect B has on A alone. Can you see? Because B, you control for that effect. So that is semi-partial. But if the B also has effect, you are controlling for effect of B on A and Y. But you are, you are interested in the correlation between A and Y. You also control for effect of the B on both of them. That is partial correlation. But if it is only on one of them you control for, that is semi-partial. I think that will stop here. That is any question you want to ask. So, I don't know if you have question.
Thank you very much, sir.
Yes, yes, I can see some chat.
No worries, sir.
Do you say that?
Sir, the question I asked, like the last time you explained, sir, you talked about bivariate zero correlation. You talked about the partial and semi-partial, and that's types of correlation. So the other one you talked about the point biserial, the biserial,
type
the
of
Kendall,
correlation
the
coefficient.
Those
one are type of coefficient.
So that's different.
Yes, okay. I said that those one biserial, point biserial, piercing, although they are type of coefficient. That is the type of correlation you are calculating. That's what I'm saying. That was coefficient, what you are calculating.
Okay.
The partial just mean that how you are calculating it. That type mean how you go about it.
Oh, I know. Okay.
So
there was this so the bivariate zero means that there is nothing.
Zero order.
No
zero,
external.
Just bivariate means zero order. Yeah, you are not trying to. You are just focusing the relationship between the two. You are not trying to see. You don't want to look at confounder. What is affecting anything? No, you're like somebody that say, I do my business, so I don't interact, I don't do this. So, but somehow, whether you like it or not, whether you don't interact, those things also affect you. You're like you that say they are not interested in politics, but politics is affecting them. It's affecting their business, it's affecting many things they do. You just say, oh, they don't get involved. They just face their business. But all those things you don't get involved in, if you don't get involved, they will affect you also. So for the fact that you did bivariate doesn't mean that those other things didn't affect. Maybe that's why they call it zero order. So they say, please, you say that is so when the data correlates after using present.
They did not want to focus on any other external variable.
Yes.
But it's possible that there might be a variable that
of course, now that is affecting it. That's why you see correlation between two things strong. Doesn't mean that both of them, there's actually a strong link between both of them. Some of the strong link may be other factors. You're like you are they give you assignment in school, and you have a roommate or a friend. Whenever they do assignment, you do your own, and that one will just collect your own also. Let me see, I will be scoring high. But when it comes to exam, if there's no room for cheating, you will not be able to score high like that, because there's no. You get it now. So you seen the person score. This lady is good. Oh, this person is good. Oh, see the score. No, that it's a friend. It's a friend that is influencing the score. It's not as if maybe that person he correlates very well with that score. Is another person that is sounding, a friend of that person, that is the one that has high correlation with high score. But because he's helping the person, that's just it.
Okay.
So,
thank you.
Okay, this I can't explain the discordant line in the candle part. The discordant line, is there any problem with the discordant line? Okay, I will go
No,
ahead.
that one where you.
I will look. So how do you interpret the test for person correlation? The test for, I've already said that is it not p-value? If you calculate the t, you go and look for the p-value. Even if you run it with SPSS, this is give you the p-value. It will not show you any t. It will just give you the p-value. You know the p-value. But we say I say that the p-value is useless. It's not useful for anything because of the way it is affected by the sample size. So the p-value is not useful. So you say that it is when the data is not correlated after using person that you go with SPEMA. No, we said that SPEMA spacing is more for continuous variable. If the variable does not form low manner distribution, it's not if it's a RAM variable or something that is discrete. It's better you don't use. So if you have one discrete, one continuous, you can still use person. But in a situation where you are having one that is order, categorical order, rank, it's better you use SPEMA. Then Dr. Lara for okay. Thank you, sir, for the lecture. Can I explain the low positive and low negative correlation graph? Okay. Let me just go. Low. I think it should be this graph. What we are just saying, if you look at it, it's scattered. If you see both of them, they move. You can see this one is going up. They are not. Are they all on the straight line? They are scattered. And this one is more. This one 0.5 is more scattered than 0.9. So it shows that the one that is less scattered is stronger. This one is the strongest, perfect. All of them are on straight line. This is a perfect. This is strong, high. This is like moderate. So these three now, they are positive in the sense that they go up. That is, as one, both of them increases. As this one is increasing, this one is increasing. As this variable on the vertical is increasing, this one on the horizontal is increasing. That's why the graph is going. You know, when you are talking of graph, where they meet is the 0 point. It is assumed that whatever you are measuring on the horizontal is increasing along the arrow, in the direction of the arrow. While this one along the vertical is increasing the direction of the arrow. So the point is where this point is where both value meet, both horizontal and vertical value. So for this one increase, and this one increase, both of them are increasing. You can see where they meet now, along the something they are increasing. But if it is this one that is negative now, the highest point is, let's look at the higher point, this one. The highest value for the vertical now correspond with the lowest value for the horizontal. Can you see? But as this one decreases now, look at this place now. As this vertical decreases, this one increases. Can you see? So okay, the highest point of the horizontal is the lowest point for the vertical. As you try to reduce the value of the horizontal now, the vertical increases. Can you see? So that shows that they are in opposite direction. So that's why the slope go down. So all those ones that slope down, they are in opposite direction. So they work in opposite. So that's why it's negative correlation. So the direction is different from the strength. The strength is whether it's on a straight line or scatter small or scatter very well. That is the strength. The direction is whether it's going up or going down. There are two different things. So that's why you can have perfect positive, perfect negative, moderate positive, moderate negative. If there's no direction at all, in fact, that shows that both, if there's no direction, both the magnitude and direction is 0. That's just one thing. So if it's scatter, number one, the correlation is 0. In value, no direction. That you can see, just the scatter. I think that one is answered. So the person that
Thank you
was,
very much.
yeah.
Okay.
So the person that was asking for, I think is talking about, somebody was talking about this discordant. You understand the concordant? The discordant is the opposite of the concordant. If you look at it, you are trying to check each of the second ranking, the second. You are trying to check it against the first. Concordance, you are checking if any of them are more than what you have chosen the second, where level you are. For the first one now, anyone above this one, that is, apart from this line, the line of this first one, on the opposite side, anyone above the value, how many of them are above that is the concordant. The number that are above are the concordant. But the discordant, the number that are below or equal to, that's the discordant. Like for these two now, when you choose from here now, this line down, it's only this two that is equal to these two in value. Among all the 11, from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 of them is only two that is equal to or below the two. So that is why it's 1. Here, for this one now, when you start moving from 3 down, there are 10 of them. None of them is below or equal to this one. That is why it's 0. When you choose this one now, this 4 now, when you choose from here down, all the 9 of them is only this 4 that is equal to or below 4. So that is why it's 1. When you choose this one, among all this one, 8 of them down, there's none that is equal or below 3. That's why it's 0. The same thing like that. That is the way the disc corner. And once you're able to do that, but it's just the logical. Because,
thank you, sir.
Yes.
I understand.
Yes, just the logic. Just for you to know, if you, in fact, to run correlation is the easiest to do, because you just go correlation, you just move those things inside. The computer will give it to you. All this one is just for you to have a mental picture of the logic behind it. So any other question? Any other one? See? Okay, no question. So if there's no question.
Thank you, Dr. Lolako.
Yeah, welcome.
Well done.
Thank you.
I said I was surprised. Yeah, what I have a standard there. I don't know whether it's seen.
Well, let me see.
I said I was surprised reading in a standard textbook.
I was surprised to read the standard about
in a standard
EV and IV for correlation.
Dependent and
People
independent
talk
for
about
correlation.
yes and correlation between continuous and categorical. No point by serial mention. Can we come? Okay, yeah, you can see. Know that even if you want to start talking about partial, semi-partial, you will see something like DV, dependent variable, independent variable. You'll be seeing it like that. So that one on the lighter note, it's not as if, because correlation, you can, not that you cannot do, even when we interpret regression, we look at the relationship between X and Y. X the independent variable, Y dependent variable. If you look at it, correlation is very useful in interpretation because the square of correlation is the R square is the coefficient of determination. So even for you to have a relationship, there must be the association. Then what is there is that it's not all the situation. So there are situations that you just do correlation most of the time. They don't even have anything in common and they will correlate. And that is why people say that in correlation, just forget about dependent and independent variable. But not that if you know that this particular variable, they are dependent and independent variables, not that you cannot think of their correlation. For example, now, people know that salt intake and blood pressure, there's a relationship. So you can think of, if you are still thinking about the correlation, of course, if you want to even do this scattergram, it will still make sense to make sure that the independent variable is the X and Y the dependent variable. So when we even start talking about the partial correlation, semi-partial, People use the word dependent, independent variable also. So that's just it. And another thing is that when it comes to the field of research, the rigor, some people, different people put different rigor into research and statistics. The reason is that some people need it more. The people doing physics, chemistry now, they don't, most of the time, they don't matter too much on statistics. Because most of the thing they measure, they can see it. They can, what they are looking for, they see it most of the time. In fact, if they don't see it, they know that they made mistake. If they say that hydrogen react with this thing, it gives green color. So you go and do it anywhere in the world, you get the same thing. So apart from taking measurement many times and calculate the average, I don't think they need any much statistics in doing their own work. And that's why we, the biologists and the social scientists, because we have spurious, very the variable that follow probabilistic model that is very random, too random, and just take any value anytime. Those variables will not depend on statistics, and that's why in our own field you see a lot of exploits in statistics, and many people also bring a lot of knowledge. Some people can publish some things also that some people will say rubbish. As you are going higher, you discover that you see a lot of issue, divergent opinion concerning something. For example, we talk about the gate correction. Some people feel like nonsense. What are you correcting? But the person that corrected was one respected Professor Yates. But some people say that the chi-square is already conservative. Why are you correcting? Some people don't believe. Some experts also don't believe in it. There are issues about when we use this p-value you are talking about. Is it when it is less than 0.05 or at 0.05? Is 0.05 or less or less than 0.05? You see, some people say it's when it is less than 0.05. Some people say it is when it is less than or equal to. But I'm one of those people that say it is when it is less than or equal to, because when you are talking of 95% confidence interval, so less than we correspond to less than 0.05, we correspond to more than 95% confidence. So if you are talking of 95% confidence, it's 5% that correspond with that. So me, I believe because of that, 5% is part of it. If my p-value is 0.05, it's significant. The logic behind is 1 out of 20. So those are the things. So at high level, people have direct opinion, but those ones, so most of the time, they are not so important. They are not important issues. They are not critical issues. So that's just it. I think I've answered your question, sir. Like for example, issue of by multivariate analysis, multivariable. Many people call, but it doesn't change anything. If somebody did the regression, say call it multivariate and tell you that really know what he's saying that it's multivariate, it doesn't do any harm. So far they're able to provide solution. But me, I mean, I said, oh, it's not actually it's multivariable. The one that are multivariate and multidimensional scaling, they may not know about that. It doesn't remove anything. You don't need to know everything in life. So that's just it. So at high level like that, divergent opinion and all those stuff. So any other one? So we'll continue this week with you. Let me see.